Writing proofs is possibly the most complicated topic in geometry. So here are the basics of how to write a two-column proof. So here's the first example of something that we're going to have to prove using a two-column proof. The point of every proof is to prove a statement. So for example, for this one, we have to prove that angle 1 and angle 2 are congruent. That's what this little sign means. It means congruence. And all we get is what it says here, which is the given information. So all we know is that angle 1 and angle 2 are right angles, and we have to prove that they're congruent. Now, at first, this might actually not seem that hard. Remember that right angles are 90 degrees. So if they're both 90 degrees, then that means they have to be congruent, because congruent means that they're the same amount of degrees. But the annoying part of a proof is you can't assume anything. You can't skip any steps in your thinking. Every single thing that you did to get from here to here, you have to explain it and give the reason for it. So the way that we're going to do that is by using two columns. So we're going to draw what looks like a T over here to the right. So the left side of your proof is going to be all of your statements. So what we're going to do is we're always going to start with our given statement, which is angle 1 and angle 2 are right angles. So at the top here, I'm just going to put a 1 because it's step 1. And I'm going to write this down. Angle 1 and angle 2 are right angles. And basically our goal with the left side is we're going to keep writing different statements that have to be true. So because angle 1 and angle 2 are right angles, something else has to be true. And because of that, something else has to be true. And because of that, something else has to be true. And eventually at the bottom, we're going to have our proven statement, which is that angle 1 is congruent to angle 2. This is our bottom statement. This is what we're trying to prove. And all we have to do is just connect the dots. And notice how I'm not putting a number here yet because I don't know how many steps this is going to take. Some proofs only take like one step in between. Some take 3 steps in between. It's totally different. Now, you can't just connect them with statements. You also have to explain why that statement is the case. So on the right side of our proof is going to be our reasons. Every time we write a statement, we have to state the math rule that explains why that's true. The first statement is always the easiest to come up with a reason with. The reason that statement 1 is true is because it was given to us in the problem. So for that case, you can just write the word given. We only know that this is true because the problem said it was true. So you always start with your given statements. But for every statement that we say from now on, we have to have a reason. Now, you may not have realized it, but remember when I explained why this was really obvious? I said angle 1 and angle 2 are right angles. Right angles mean that they're 90 degrees, and 90-degree angles, if they're both 90 degrees, then that means they have to be congruent. When I explained that, I just explained the entire proof. So for the proof, we just need to write that explanation out, but as specifically as possible without skipping any steps. So what was the first thing I said? The first thing I said is, well, right angles mean that they're 90 degrees. And that is something that we have to say. We can't assume that the reader knows that right angles are 90 degrees. We have to put that down. So in this case, because angle 1 and angle 2 are right angles, that means we know that the measure of angle 1 has to be 90 degrees. And we also know that the measure of angle 2 is 90 degrees. But remember that you can't just put the statement. You have to explain why that's true. But in this case, that's not too big of a deal. Literally, the reason that we know this is because that's what a right angle means. A right angle means that it's 90 degrees. So on the right, we're going to put that it's the definition of a right angle. Now, you might be tempted to just skip over to the next step and say, well, see, angle 1 is 90, angle 2 is 90. That means they're congruent because they're the same amount of degrees. But actually, that's skipping a step. We skipped over the step that says that because angle 1 is 90 and angle 2 is 90, that means that angle 1 and angle 2 are equal. I know this seems completely pointless, like of course they're the same number, that means they're equal. But that is another step that you have to write down. Remember, you have to write down every step. But now what is our reasoning for this? I mean, it seems kind of weird. Like, what are we going to write down for this? Like, that's what equals means? So for some reasons, you're actually going to have to put the name of a math rule. And usually your textbook will have like a big list of the different math rules, or it'll say like, this is a postulate or this is a theorem. Those are names of math rules that you need for proof. So for this one, this is actually going to be the transitive property of equality. And if you have no clue what that is, let me go ahead and explain. So the transitive property of equality says that if A equals B and B equals C, then A equals C. So like just to give an example of that, let's say that we knew that X was equal to 5. And let's also say that we knew that phi was equal to y. Well, the transitive property says that if we know that x is the same as 5 and 5 is the same as y, we can just ignore the 5's and just say that x is equal to y. So that would be another statement that would be true. So I want you to think about how that applies to this statement here. Well, we have two statements. We know that angle 1 is 90. And for the sake of just making this look easier, let's go ahead and flip this around. We also know that 90 is equal to the measure of angle 2. So the transitive property says that we can ignore the 90s and just say that angle 1 is equal to angle 2. I know that this seems like a super overly complicated way of just saying something so basic, like angle 1 is 90, angle 2 is 90, so they're equal. But we have to overcomplicate everything in proofs. We have to explain every single little detail. So now the only thing that we have to decide is, can we just go from this statement to saying that they're congruent, or do we have to put in another step? Well, what is the definition of angles being congruent? Angles being congruent means that they're the same amount of degrees. And that's exactly what statement 3 over here is saying. It's saying that the measure of angle 1, or its amount of degrees, are the same as angle 2's amount of degrees. And that's literally the definition of being congruent. So this will be our final statement here. And our reason is that it's the definition of congruence. So let's review our proof here. We started with angle 1 and angle 2 being right angles. That was given to us by the problem. Based on that, we knew that both angles had to be 90 degrees. That's the definition of a right angle. Then we knew that because both of them were 90 degrees, that means that they have to be equal to each other, which we had to prove really dumbly with the transitive property of equality, but we got there eventually. And then finally, we knew that that was literally the definition of angles being congruent, which was statement number 4. So once you've successfully connected the dots between our statement that was given to us in the problem to the statement that we're trying to prove, then that's how you know your proof is complete. So here's another example of a 2-column proof. this one we have to prove that AC is equal to BD. This one's gonna be a little bit harder, but we're gonna do it the same way. So remember that at the end, we have to prove that AC is equal to BD. This is going to be our final step, and this is what we need to connect to. But this one seems kind of weird because we don't have any given information, right? It just says prove that AC is equal to BD. So what do we put to start? Well, we actually are given information to start. It's just not in letter or word form. Instead, it's in the form of these little pink lines. Whenever you see two tick marks on two different segments of a geometry picture, then that means that they're the same length. So we actually are given information to start. We're told that the distance between A and B is the same as the distance between C and D. So we can actually use that as our first given statement. So our first step in our proof is that AB is equal to CD. And our reasoning for that is it gave us that in the problem. Now we need to go to the next step. We can't immediately jump from here to here. I know they look kind of similar, but what it's actually saying is we need to prove that AC, which is this, is equal to BD, which is this. Now, just looking at this, I want you to think about how you might go about proving that this is true. Well, just generally from this, I'm noticing that AC and BD share the same line. They both share this part here. And actually, if you were to take this shared part out, then all you would have left is AB and CD, which we know are the same. So I feel like this proof is probably going to involve both of these having BC in them. So first of all, let's go ahead and prove that AC includes BC. And the way that we do that is by splitting it up into its two parts. So AC has two parts to it. It has AB, and it's added to its second part, which is BC. But remember that you have to give a reason for everything. And this statement here actually has a name. The rule that says you can do this, the rule that says that two smaller parts are added together to make a bigger part, is called the segment addition postulate. I think the reason that these proofs can seem really scary is because we always have big, complicated names like segment addition postulate in our proofs. But you have to remember that these complicated names are usually just the names for simple statements that like you can add two smaller parts to make a bigger part. That's actually exactly what the word postulate means. It just means something that's really obvious that we don't need to prove. If you weren't sure that this was called the segment addition postulate, I actually have a video on it that you can watch if you want to. So we've just proved that AC includes AB and BC, but we can actually do the same thing for our other part here, which is BD. So let's go ahead and write another statement that says the same thing. So BD is actually two separate parts. It's BC here, right? And it's CD. And the rule is exactly the same. It was the segment addition postulate. Now, it seems like we're still pretty far away from proving that AC is equal to BD, but we actually only have one more step. And for this step, we're going to need to do a little bit of algebra. You don't just have to use geometry in your proofs. You can also use algebra in your proofs. So always remember what we're trying to prove. We're trying to prove that AC is the same as BD. And we know that AC is this and BD is this. So how could we possibly prove that this here and this here are the same, that they're equal? Well, it might not be immediately obvious, but we actually haven't used our given statement yet. So far, it hasn't been useful to us that these two are the same length. So let's use this statement now. What if we had AB equals CD? And what if we added this middle part to both of them? Because remember that we said that this proof is probably going to involve both of them having BC. So what happens if we add BC to both sides of our equation? Because remember, in algebra, you can always add something to both sides of the equation. Well, before we formally write this down and make it neat, let's make sure that we're accomplishing something. What is AB plus BC? Well, AB plus BC is AC. That's what it says right here. So that's this. And what is CD plus BC? Well, that's the same as BD, because that's what we proved in step 3. So if that seemed a little bit confusing, maybe it would be easier to see as a picture. So remember that we started with knowing that AB was the same as CD. But what I wanted to prove was that AC was the same as BD. So what I did was I added BC to both sides. So what that did over here was I added BC to our segment and extended it all the way over here. And by adding BC to the other part, we extended it all the way across here. And this is now exactly what I was trying to prove. Just by adding BC to both segments, we've now proven the statement that we were trying to prove. So let's go ahead and rewrite this to be a little bit neater. We took this beginning statement and we added BC to both sides. Now, this rule that you can add something to both sides of an equation, that actually has a name as well, and that's called the addition property of equality. And that's actually the name for all of the properties where you do something to both sides. So for example, if you multiplied both sides by something, that would be the multiplication property of equality. Or if you divided both sides by something, that would be the division property of equality. They all kind of have similar names. And now are we done? Well, actually, we are. This is going to be our final step. And the reason is because of substitution. Earlier, we split each segment up into two smaller segments, but now at the end, we can combine them back. So AB plus BC, we know, turns into AC. And CD plus BC, as we showed in step 3, is BD. So we took something and we substituted in something else that we knew was the same. And because of that, that rule is called the substitution property of equality. And I know that it took a lot of steps, but let's go ahead and review what we just did. We started by knowing that AB was equal to CD, because that's what those tick marks meant. And we also noticed that BC, this part here, both of these had in common. So we knew that the proof was going to have something to do with that. So I figured, why don't we just split these up into their two parts? And that's what steps 2 and 3 are. We split up our segments into the two smaller parts. So the last thing we needed to do was to prove that these two statements were the same. And the way that we did that was with algebra. So we actually took the first statement again and added BC to both sides to replicate these statements. And then to finish things off, we took our split up line segments and we turned them back into just their full line segments. So I know that one seemed a lot more complicated because in the last one, we went from 1 to 2 to 3 to 4. But in a proof, you can actually also go back to previous statements and pull from those. You don't necessarily have to go in like from 1 proves 2, which proves 3, which proves 4. We actually pulled from statement 1 like 3 different times. So if you've never seen a proof before, this was probably pretty mind-boggling and you're probably still confused. So honestly, the best way to get better at proofs is to just keep seeing more and more proofs. And chances are in your geometry class, you'll probably be seeing a lot more of these. So the more that you do them, the more you'll get used to them. Practice is key. So that was how to write a 2-column proof in geometry. The chances are one of the hardest parts of proofs for you is knowing the names of all these random math rules. And a lot of the rules that I actually talked about in this video were properties of equality. So if you want to learn those properties, then you can watch this video right here. And as always, if you have any questions about this video, go ahead and leave it in the comments and I'll be sure to answer your question. Thanks for watching.